Industrial three-phase alternating current is a volatile force. When crossing large metallic contactors without precise control, it routinely arcs, seeking any available path to ground. We cannot simply wire this level of dynamic power directly into an automated production line. The phases must be structurally manipulated. To tame and route this current, engineers rely on industrial inverter drives, like the MicroMaster 430 series. Inside these units, a rectifier converts the raw incoming AC supply into a stable DC link. The inverter section then pulses this direct current to build a synthesized, highly regulated AC output. But the way this synthesized power behaves depends entirely on the physical structure of the components receiving it, the motor windings and the transformer coils. The geometric connection of these coils, specifically the delta and Y configurations, dictates everything from the torque curve of a single motor to the stability of a multi-megawatt grid. Engineering these industrial systems requires an understanding of how phase topologies actively shape the electrical pathway. Three-phase electrical windings are typically wired in two ways, the triangle-shaped delta and the star-shaped Y. In a delta topology, the windings connect end-to-end, forming a closed loop, allowing higher top speeds but less low-end torque. This chart graphs the torque capability of an inverter drive against its frequency. If a process requires high torque at low speed, the Y configuration is the preferred choice, and it operates with higher baseline efficiency. The delta design carries an operational vulnerability directly tied to its physical geometry. Because the circuit forms a continuous internal track, high-frequency parasitic electrical currents can circulate entirely within the motor, leading to excess heat and wasted energy. The Y winding operates differently. Its branches meet at a central point, but remain open-ended at the power connections. This layout physically prevents those parasitic currents from finding a closed loop to circulate in. Selecting the right motor topology forces an engineering trade-off, balancing absolute top-end speed against the daily cost of internal parasitic losses. When monitoring these systems, you cannot wire high-power industrial lines directly into delicate programmable logic controllers. Instead, the system relies on instrument transformers. Current transformers, or CTs, measure the amperage. Potential transformers, or PTs, step down the voltage to readable levels. We also gather supplementary environmental data. Differential transformers track physical displacement, while resistance temperature detectors monitor thermal conditions. Extracting electrical values requires specific geometric arrays. One method is the three-wire open delta, using exactly 3 current transformers to monitor phases. Alternatively, a 4-wire YE configuration removes the current transformers, tying 2 potential transformers to a central neutral line. This specific 4-wire YE setup with 2 PTs is mathematically required if you need to accurately capture line-to-neutral voltage readings. The physical metering topology dictates the exact data fed back to the logic controller, determining whether the drive registers a balanced grid or a critical line fault. Scaling up from the motor level, we have to look at the main infeed, the exact point where utility power first encounters the drive system. Large facilities place an isolating transformer ahead of the AC supply. This matches the incoming voltages to the equipment and filters out line noise. Crucially, this isolating transformer blocks ground currents that would otherwise flow uncontrollably through cable capacitances. To maintain a balanced current in uncompensated basic line modules, engineers specify a symmetrical 3-winding transformer, like the DY5D0 vector group. This features 1 delta primary winding, feeding 2 identical Y secondary windings. At the multi-megawatt scale, harmonic distortion is a severe threat. We mitigate this using a double-tier transformer, vector group YY6D5. Here, a primary star winding feeds 2 asymmetrical secondary windings. Winding 1 uses a star topology, while winding 2 uses a delta. This configuration produces 2 completely separate, galvanically isolated 3-phase AC supplies. By forcing power through 2 structurally different geometries, the transformer creates a precise 30-degree phase offset, causing the harmonic feedback from the 2 lines to continuously cancel each other out. Intermixing Y and delta configurations allows engineers to surgically manipulate AC waveforms to guarantee absolute stability at a utility scale. At the highest structural scale, facilities connect massive active line modules in parallel to feed a single shared DC bus. Running these units in parallel imposes a strict baseline rule. The phase connections and the physical power components between every unit must be perfectly identical. Parallel stability relies on tight mathematical constraints. The transformer's relative short-circuit voltage must be at least 4%. The difference in short-circuit voltages between secondary windings cannot exceed 5%, and the difference in no-load voltages must be strictly under 0.5%. Even the physical power cabling running between the transformer and the line modules must match exactly in length and cross-section. If any of these physical parameters vary, or if software settings like configuration parameter P076 are entered incorrectly, the system fails. Any impedance mismatch causes an unequal current distribution, triggering a runaway imbalance between the parallel branches. The hardware result of this imbalance is catastrophic. It will physically destroy the parallel unit's current transformer. In high-power parallel architecture, relentless mathematical and geometric symmetry is the only defense against structural collapse. From the internal windings of a single motor to the transformers powering an entire facility, structural geometry dictates electrical reality. At the motor level, Y configurations eliminate parasitic loops for low-speed efficiency, while delta topologies enable higher top speeds. To measure those outputs, instrument transformers are arranged into precise geometries, like the open delta, to safely interface raw power with logic controllers. Moving upstream, double-tier transformers fuse star and delta windings to force a 30-degree phase shift, canceling out harmonic feedback. And when scaling up to parallel architectures, strict threshold parameters and absolute physical symmetry are non-negotiable to prevent hardware destruction. AC power is not a raw resource to be simply utilized. It is a vector force that requires rigorous geometric partitioning to remain under control. True mastery of high-power industrial drives lies in commanding the structural flow of the phases themselves.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.